In Q-learning, you're going to usually have some rewards. Maybe there's a 100 there, maybe there's a 200 there, maybe there's a -5 here, maybe there's a wall of -1s. And so we've got all these reward spots, but then we're going to have a Q table, or a utility table, and that's going to cover every single state, and in every state we're going to have a value. And that's where we did this thing where we started propagating, put a 99 there, and a 98 here, and a 97 there. And if we get over to here, we get a 96, 95, 94, 93. What utility do we put right here?
92. No,
it's going to be an 87. But what utility should go right here?
86.
One would say an 86, but that's only if you followed this path through that -5. But you're really going to go around it because that's going to have less cost. It's going to be 93, 92, 91, 90, 89, which is better than 86. And the better ones always dominate because when you make choices, you always will choose the better one, right? So one thing you want to observe is that rewards are very attractive. They kind of propagate outward like this. Whereas penalties, they kind of don't do much. They just sit there and say, don't come here. Unless there's no way to not fall into them, in which case they can propagate a little bit. The only reason we're using a grid is because it's discretized and it's easy for humans to think in discretized space. If we were using a model to represent our table of utilities, like a neural net, this whole thing would be a continuous field. So this doesn't have to be a grid. It doesn't have to be 2 dimensions because there isn't just hunger and temperature, right? Those are just 2 things that you have to balance. But in life, you're really balancing hundreds of things. And there are actions you can do in all of those hundreds of dimensions. There are lots of actions you can take. So really, while I'm drawing a grid, I really want you to be thinking of a function here, something that takes an arbitrary number of inputs and then outputs some measurement of utility, contentment, happiness, homeostasis. And the whole point of Q-learning is we're going to find the optimal choices that will maximize your contentment in all of the dimensions that you're using in your model. Okay, we talked about how you could start with these rewards and the value propagates out from them and it fills up the whole board, the whole table with these numbers. Imagine that you're training a robot. This is the starting position, but from that starting position you're trying to get to this ending position, which means this is dirty dishes and this is clean dishes. Do you see that you can try actions? You can go from that starting state to all of the adjacent states. But there's no way you can just say teleport to over here, right? That state might represent the dishes being all neatly stacked over here. And how do you tell your robot, just go to that state? You can't. Yeah. There's no way to do it. You can only find a path of actions that hopefully gets to that state. So what we need to do is find a way to do this propagation without being able to just visit every state. And that's what Q-learning does. Here's how Q-learning works. Suppose you're a robot and you start right here. You can go to any of these spots. Maybe we go to this one. And then maybe we'll go to this one. And then this one and that one and that one and that one and then that one. We could randomly walk through our space if we wanted to, right? And every time we did, we could take the value that was there and propagate it back 1 step, because we have seen the next state and we've seen the previous state. But you can imagine that as the robot wandered through its states, the values would start to propagate just along the path the robot followed, right? Well, what if the robot wandered for all of eternity? Eventually, it will have hit every state hundreds of times, right? Thousands of times, millions of times, and we'll have made every possible transition. And so eventually, those values will propagate all over the board as if you had just visited every single state systematically and made them propagate. So we've taken what was a very computationally expensive operation. We already know searching is expensive, right? Because you have to visit all the state space. Well, reinforcement learning is even more expensive because you have to visit the whole state space a whole bunch of times until the values propagate around. Q-learning is even more expensive than that because you have to randomly wander through your state space so long that it's as if you had visited every state a whole bunch of times, such that the values have all propagated. And the reason we do that is because we're assuming the limitation of you can't teleport. You can only wander through your state space, which is a very real-world limitation for a lot of problems. But essentially, if you were to do wandering forever and propagate every step that you take, then the whole chart will eventually converge to a fully converged table of utility values. No, because imagine you're really far away from the reward.
Right.
The value that your neighbors have might not yet be fully converged.
Yeah.
And so you need to end up visiting everything a very large number of times until nothing is ever changing anymore. When nothing changes and you can wander anywhere in your state space, then you can say that these Q values have become utility values, and at that point, whatever your policy says to do is the truth, the best action you could possibly take. So, long story short, Q-learning is a very computationally expensive way of doing utility theory, but it works in these environments where we have the inability to teleport to random states. All we can do is wander and see what happened and learn. And so it's a surprisingly capable algorithm. It's just darn expensive. So, your assignment will be to implement Q-learning. What you do in Q-learning is, well, we're going to work with a grid world. Not this one. I'm just not illustrating well today. But imagine a world of grid. We'll look at this one. Here is a grid world. You're going to make a very simple grid world like this. I don't think I need to provide any code for you to do that. It's going to be easier to just make your own. Make a grid world and make a agent which will wander through this world. That agent will wander randomly. So you'll have an X and a Y position, right? And at any moment, if you were right here, you could add 1 to your X, or subtract 1 to your X, or subtract 1 from Y, or add 1 to Y. You should be able to go to each of those directions. And as your robot wanders around through its world, or as your agent wanders through this grid world, each time whatever value is there will propagate to the previous one where it was. Okay? Now at first it'll be full of zeros, and so every step you take will propagate a 0 to a 0, and it'll do absolutely no good. But once it eventually finds the goal, just through sheer luck, then those values will propagate to the adjacent ones. And then after it does that enough times, those values will propagate all throughout the map, and eventually the whole map will be full of meaningful values, and then the agent will start behaving intelligently. Now we arrive at the meat of the lecture today. Let's talk about this equation. This is the propagation equation, or the Q-table update equation. This is the one that takes, I was here, I'm going there, here's what I observed, here's how I learned from it. And if you can understand this equation, then all of Q-learning falls into place, and then you're ready to code up this assignment. Q is the table, by which I mean this is the, Q is your policy function. It is that whole, this function. It's this one. Right? It's the function that maps from state to contentment. And this is the thing that we want to learn. Q could be represented with a neural network or a decision tree or anything else if you wanted to, but we're just going to do it with a table because it's easy. If you want to implement it with a learning model, that would be even more awesome. Okay, I is going to be what I'll call the previous state, meaning if your robot was in this state and it transitioned into that state, so you're going from here to there, then this one would be state I, and this one would be state J. So we might further come down here and call J the current state.
Oh, that's state is just a position, basically?
Yeah, so when I say state, it's not a number, it's a vector. It's all the numbers necessary to represent your state. In your assignment, I will be an x and a y value, and j will be an x and a y value. So there'll be two-dimensional vectors. If you were doing a robot with 20 joints, these would be 20-dimensional vectors just to represent the pose of the robot, plus a few more values to represent the state of the world, the environment in which the robot exists. So I and j are vectors of whatever size is necessary to represent the state of the universe. A stands for action. This is the action that you are going to, this is the action that you took in state I. Yeah, this is the action that you took from state I to reach state j. So I guess I should notate a letter A right here to say the action is what caused you to transition from I to j. This arrow right here is the assignment operator. In most programming languages, that's the equal sign. It just, we're updating the value in the table. Notice that it reads from the table in order to update the table. So we're actually going to see what's in some other cells in the table and combine those values to put them into this cell of the table. That's because we already have some utility value here in state j, and we're going to read that utility value and then discount it a little bit and then update the value in state I. So we're basically saying when the robot or agent steps this way, the values propagate back that way. Does that make sense? If I was right here and I go to right there, I just learned something. I learned how awesome it was to be right here. Because, hey, once I got right here, I got a donut or something like that. And because I got a donut, now I'm super happy. Then I etch into my brain, hey, remember that time when I was way back here and I almost got a donut? That was awesome. Because then I just had to go like this and get a donut. Does that make sense? Because I got a reward for being in state j, I know that state I is nearly that reward. It is a little bit awesome because I can get that reward. So there is a thing right here called the discount factor. And the discount factor says how much your value decays over time. In the example last time, we just decayed by 1 because that made the math really easy and kept my numbers clean. In Q-learning, we're going to decay it by a scalar value, which is the parameter gamma. That's the Greek letter gamma. And this kind of makes sense in life in a lot of ways because value tends to decay exponentially in most circumstances. Think of it as interest, or think of it as, I don't know what you want to think of it as, that's just the way we're going to do it. Plus it makes the math work out really nicely. So gamma is some discount factor. What's a good value for your discount factor?
0.95.
I don't know. Something big, something close to 1. 0.9 might be okay. 0.95 usually works well. 0.99 might be a good one. You don't really want to go bigger than that. Here's why. If you went all the way to 1, that would basically say a bird in the bush is as good as a bird in the hand. Meaning, if you could get a future reward, get one now. That would mean, that would be those children in the marshmallow experiment who would sit there for 20 years to get that second marshmallow rather than eat the one marshmallow now. You see what I'm saying? A 1 means the future is just as good as the present. And that's not very realistic, is it? If you were in the Harvard marshmallow experiment and you could get 2 marshmallows in 20 years or eat 1 marshmallow now, which would you pick?
That's 1 marshmallow now.
Everybody would want the 1 marshmallow now, because 2 marshmallows in 20 years, come on. That's dumb. Whereas, hey, you can eat this 1 marshmallow, or you can wait for 2 seconds and then get 2 marshmallows. Who's going to eat their marshmallow? Of course you're going to wait for 2 seconds, because that's not a big deal. 2 seconds is better. So humans seem to have some concept of a discounted reward system in their minds. Don't you agree? And how you tune it, adjust that. If you set this all the way to 0, then that's the child that says, hey, would you like a marshmallow now or a marshmallow in a nanosecond, or 2 marshmallows in 1 nanosecond? And the kid says, 1 marshmallow now. Because the immediate reward is so much more valuable than the future. This is a untrusting child who can't see future value. A value that's close to 1 basically says the future is important, but not quite as important as the present. And that seems to be the best way to discount the future in order to make the agent behave intelligently. And you can adjust this number, and you should adjust this number, because if the agent is too scared of these penalties, the agent might just cower in its corner and not go for the goal. And that actually can happen, because it can be so not worth it to go for the goal because you might get a penalty that it's actually a wiser decision to just sit there. And you'll need to adjust some of these values to make yours work. So I want you to have some intuition behind what the numbers do and how they work. Yeah, I'm going to let you control your rewards. So this is your reward function, by the way. And this function here says, what is your reward for being in state I and doing action A, which causes you to transition to state J?
So that's the value that's propagated.
Yeah. So why all of these parameters? Because if you wanted to, you could have your reward based on what action you performed or what state you were in or what state you landed in. In our case, we're just going to have the reward only depend on the state you land in. So you can cross out these 2 parameters if you want to. It's just there to show you that you could have your reward depend on anything you wanted it to. This whole term is the reward you get for landing in state J. Yes?
How do we determine that?
How do you determine that? That's going to be something you get to determine. Suppose you set a reward of 1 every time you reach the goal. Well, if your penalty for hitting a wall is 0.00001, then surely the agent will see that 1 is much better and will go for the goal. If the reward for reaching the goal is 1 and the penalty for hitting the wall is negative 1 billion, I bet you the agent will cower in its corner because not worth it to even risk going near one of those walls. And if you were to adjust them proportionally, it should work.
Like the normal one would just be 0.
Yeah, there's not really a scale. You could go from 0 to 1, you could go from 0 to 1 billion. And as long as, well, the agent is going to do whatever action is to its utilitarian advantage. So it's up to you to grasp the concepts of utilities and adjust them proportionally until the agent behaves intelligently, and then you've done it. I like to set the goal to be 1 because that's a good number, and then go from there. But however you want to do it, it will be fine.